Greetings everyone. NVIDIA's new neural engine is going to shock the entire real-time graphics industry. The article and the original video link will be in the description. Let's see their supplementary amazing video while listening the paper from a reporter-style voice.
According to this paper, a complete system for real-time rendering of scenes with complex appearance, which was previously reserved for fly use, has been introduced. This system is a result of a combination of algorithmic and system-level innovation. The appearance model of the system incorporates learned hierarchical textures, which are interpreted using neural decoders, producing reflectance values and importance, sampled direction. To enhance the modeling capacity of the decoders, two graphics priors are equipped. The first one facilitates accurate reconstruction of mesoscale effects by transforming directions into learned shading frames, and the second one allows the neural decoder to perform importance sampling efficiently by incorporating a microfract sampling distribution. The resulting appearance model allows anisotropic sampling and level of detail rendering, and enables baking deeply layered material graphs into a compact, unified neural representation. By exposing hardware-accelerated tensor operations to ray tracing shaders, the system has made it possible to efficiently inline and execute the neural decoders inside a real-time path tracer. The scalability analysis of the system with increasing number of neural materials has been carried out, and a proposal to enhance the performance using code optimized for coherent and divergent execution has been made. The neural material shaders of this system have been reported to be over an order of magnitude faster than non-neural layered materials. This development opens up the possibility of using film-quality visuals in real-time applications such as games and live previews. In conclusion, the system utilizes appearance models, neural networks, and real-time rendering to achieve a breakthrough in the field of graphics and visual effects. According to this research, advances in rendering algorithms, light transport methods, and ray tracing hardware have significantly improved real-time image quality. However, real-time material models have not kept up with the progress, as highly detailed materials and complex node graphs used in offline rendering are often too expensive to be used in real-time applications. In addition to computational cost, sophisticated materials pose challenges for importance sampling and filtering. Recent work in neural appearance modeling has shown promise in addressing these challenges. Multi-layer perceptrons have been effective in appearance modeling, importance sampling, and filtering. However, these models do not yet support film-quality appearance in real time. The goal of this paper is to develop a scalable solution to render film-quality materials used in the VFX industry in real time, despite the challenges posed by high-resolution textures and layered reflectance components. The approach involves baking reference material into a neural texture interpreted by neural networks, sacrificing editability for performance. The model consists of an encoder and two decoders, with the neural texture in between. The encoder maps breadth of parameters to a latent space, and the latent texture is decoded using two networks for evaluation and sampling. Algorithmic innovations involve embedding fixed function elements or graphics priors in the two neural decoders to efficiently utilize the limited expressive power of small networks. A method for inlining fully fused neural networks in rendering code is also presented. This is the first complete and scalable system for running neural material shaders inside real-time shading languages. The execution model efficiently handles divergent code paths and allows fast inferencing in any shader stage, including ray tracing and fragment shaders. The system can render complex materials that are the norm in offline rendering and achieve the visual fidelity of highly detailed assets with layered materials. The joint evolution of models and systems is crucial to bringing neural shaders to real time, and this paper provides a solid foundation for such developments. Moreover, the authors aim to provide an optimized representation for fast rendering, which is achieved by baking the reference material into a neural texture interpreted by neural networks. The resulting model is a system that fits their criteria, but it naturally comes with limitations which the authors hope to address in future work. The model consists of an encoder and two decoders, with the neural latent texture in between. The encoder maps a bird of parameters to a latent space, which is then converted into a single multi-channel latent texture. The latent texture is decoded using two networks: an evaluation network that infers the motif value for a given pair of directions, and a sampling network that maps random numbers to sampled going directions. The authors introduce several algorithmic innovations to support materials with high-resolution textures. For example, they embed fixed function elements, graphics priors in the two neural decoders, such as a standard rotation operation between trainable components of the BreeDF decoder to handle normal mapped surfaces. They also utilize a network-driven microfacet distribution for importance sampling. These priors are necessary to efficiently utilize the limited expressive power of small networks. At the system level, the authors present an efficient method for inlining fully fused neural networks in rendering code, which is the first complete and scalable system for running neural material shaders inside real-time shading languages. The author's execution model utilizes tensor operations whenever possible and efficiently handles divergent code paths, allowing fast inferencing in any shader stage, including ray tracing and fragment shaders, which is essential for adoption in game interactive applications. The authors demonstrate graceful cost scaling in scenes with many different neural materials running inside a real-time path tracer. The neural model has a fixed evaluation cost, independent of the material complexity, allowing them to render complex materials that are the norm in offline rendering. To demonstrate this, they authored several highly detailed assets with layered materials that provide visual detail down to a 10 centimeters viewing distance. They were able to reproduce the visual fidelity of such complex assets, with shading being up to 10 times faster than the original, moderately optimized shading models, while also providing additional sampling and filtering facilities. The author's work represents a significant step forward in rendering film-quality materials in real time. By developing a system that is both efficient and scalable, the authors have laid a solid foundation for future work in this area. They believe that the joint evolution of models and systems is crucial to bringing neural shaders to real time, and they have built their system to serve as a platform for this evolution.